So now that you know about equilibrium, aren't you in equilibrium right now? Probably, unless you're like exercising and jumping around while you're watching this. You're probably in equilibrium right now. For example, I'm sitting in a chair, or maybe you're standing up watching this. Uh, what force is balancing your weight? Earth's pulling you down with its gravity. What force is preventing you from falling downwards? Well, this is what we call a support force. A support force is an example would be a book resting on a table or you standing on the ground. The book, let's say, the book on a table, it compresses the atoms in the table slightly. And those compressed atoms push back up on the book and they produce what we call a support force. So you can think of it, so when you stand on the ground actually compresses under you slightly and gives an upward push. It's kind of like being on a trampoline, where then it's very obvious that it sags down and pushes back to hold you up. But the same is true even on like a hard floor. The atoms are compressed down a little bit and they push back up on you. Another name for a support force, it's also called a normal force. Normal force. Normal is a word which means perpendicular, and these forces of support are perpendicular to the surface itself. So a support force is a kind of contact force. You know, you don't feel the floor unless you're touching the floor, right? That's very different from gravity. With gravity, you know, here's the Earth. An astronaut can be way out here and feel the pull of the Earth at a distance. That is a force that acts at a distance. That's how gravity works. But support forces are ones that require direct contact. You only feel it when your feet are touching the floor. Another thing to note is that support or support to contact force, it does not have to point up or down. Okay, a normal force can point horizontally as well, or really in any direction. You know, I can push against a wall, and the wall compresses in and pushes back the other way and supports me, prevents me from falling through the wall. So don't think that normal forces are always, you know, up or down. When you stand on a scale, aren't you in equilibrium? Sure, you're just at rest. In fact, your weight is being exactly countered by the support from the scale. That's how a scale can read what your weight is. You know, a scale's not really smart and it can't look at you and figure out what your weight is or something like that. All the scale knows is how hard it has to push because the scale gets squeezed and compressed and it measures it with a spring. And the compression of the scale is what lets it gauge what your weight is. So it's because of equilibrium that the support ends up balancing your weight. In this picture, it's not drawn as a proper force diagram. Let me do that off to the side. So you've got your weight. That's your weight. You'd like to know what your weight is. You do it by standing on a scale, which gives a normal force or support force, which exactly counters your weight. They're just opposite forces when you stand on a scale, and really all the scale knows is to report that number, what the support is. It doesn't always give your correct weight. For example, what if you tried to do it on quicksand? Wouldn't the scale be sinking downwards? And in that case, the support would actually be smaller than what your weight actually is. Okay? So it's not true that the support force is always equal to your weight. Normally it is. If you're just standing on firm ground, then sure, the support's going to balance your weight. If you're on quicksand, it's not going to give the right number. Also, if you're in an elevator, the elevator is launching upwards. then the support is even bigger than your weight. And we don't want to always think that the force of support is always just equal to your weight. That's only true in equilibrium, where the forces balance. Okay. Puzzle. If you stand on 2 bathroom scales, with 1 foot on each scale, but with your weight not evenly distributed, what rules must the scales follow? Pause it and think about that. Here it is in multiple choice form. Superman's standing like that. He's standing like in an uneven fashion here. And if there are 2 scales, 1 under each foot, what's always true about the readings on those scales? This one and that one. Does each one read your weight? Each one reads half your weight? Or you add the 2 to get your weight? Okay. Pause it, think about it. Here's the answer. Superman is in equilibrium. If you stand on 2 scales, you are in equilibrium. The meaning of that is, if you stand on 2 scales, there are now 3 forces on you. The 3 forces are, your weight is one of them. That points straight down. There's your weight. And there are 2 forces that act on each foot upwards. One from that foot and another one from the other foot. You're standing unevenly, so one foot's holding up more force than the other. The rule is those 2 supports, N1 and N2, together must add up to get your weight, right? That way you'd be in equilibrium. If they both equaled your weight, then you'd have too much upward force on you. You have to add the 2 to get your weight. So it's just another case where, don't think that just because you stand on a scale, the scale is going to read your weight. If one foot's on one scale and another's on the other, you have to add up the 2 readings to get your weight. Okay, some review here. A bowling ball is in equilibrium when it's at rest, when it moves steadily in a straight line path. Both of those are none of the above. If you said both of the above, you're right. A bowling ball at rest, sure. The forces on it are the big weight of the ball and the support from the floor that's holding it up. We label it N for normal force. But even if the ball's cruising along, gliding along the floor, the forces are exactly the same. Remember, there is no force along the motion. If something's just moving steadily along, it doesn't take any force to do that. And the force diagram's the same. It's in equilibrium in both cases, at rest or moving steadily in a straight line path. These are just the 2 types of equilibrium. Static equilibrium, where the object's just staying at rest, where the ball is just staying on the floor, or dynamic equilibrium, where the ball is in motion, moving straight and steady. That's equilibrium too. Aristotle thought for anything to move, there has to be a force acting on it. Galileo demolished that idea. He said, no force on something means it'll just continue its state of motion. Okay, this completes chapter 2. There are some more review questions, which I'll go through when we meet, face to face. And we've learned about equilibrium in chapter 2. Moving forward, we want to talk about things like describing motion in detail and describing what happens when things get out of equilibrium. What if the forces are not balanced? Then how does the object move?